I welcome you to EvoStar 2007. Welcome to Valencia. In choosing Valencia as this year's location of EvoStar 2007, we've made an excellent choice. Our local chair is Dr. Ana Esparcia Alcazar. Ana has done an excellent job organizing this year's EvoStar, and I'm sure you'll have a wonderful time here in Valencia. EvoStar 2007 consists of 3 conferences: EuroGP, the 10th European Conference on Genetic Programming; EvoCop, the 7th European Conference on Evolutionary Computation and Combinatorial Optimization; EvoBio, the 5th European Conference on Evolutionary Computation, Machine Learning, and Data Mining in Bioinformatics. Along with these 3 conferences, we'll also be having a total of 8 workshops: EvoComNet, EvoFine, Evo IASP, Evo Interaction, Evo MuseArt, Evo PhD, Evo Stock, and Evo Translog. This year is an anniversary event. It's the 10th anniversary of EvoStar. It has been 10 years since the first EuroGP, the first European workshop on genetic programming, took place in Paris, France in 1998. It was organized by Wolfgang Banzhaf, Riccardo Solé, Marc Schönauer, Terence Fogarty, and William Langdon. Now here you can see a couple of slides from 10 years ago. Here's Riccardo Solé, Marc Schönauer, Michael O'Neill and Conor Ryan, and of course, Jennifer. Since then, the number of submissions have continually increased. For this year's EvoStar event, we have a total of 374 papers which were submitted for review. 163 were accepted for publication, giving an overall acceptance rate of 44%. We have 201 attendants from 35 different countries, from Australia to the United States. Here you can see the distribution of attendance according to country. Most attendants, of course, are from Spain, which has 26 attendants. Also 26 from the United Kingdom. We have 15 from Italy, also 15 from the United States, 13 from Ireland, and 11 from France. We have attendance from New Zealand, from Australia, Malaysia, South Korea, South Africa, Brazil, and Mexico. So it's almost the entire world has come here to Valencia. The technical papers were reviewed by 285 reviewers from 36 different countries, from Australia to Vietnam. Again, you can see the distribution of reviewers according to country. Of course, most reviewers are from Europe. And apparently, it seems that most experts on evolutionary computation seem to be located inside the United Kingdom, which has 56 experts on evolutionary computation. The United States has 35, Germany 25, Spain 22, Italy 20, and France 17. We have reviewers from New Zealand, Cambodia, Vietnam, Indonesia, China, Brazil, and Mexico. Before continuing with this conference and continuing with a technical session and the first invited speaker, I would like to give a short tribute to Dr. Lawrence Vogel, who unfortunately passed away in February of this year. Dr. Vogel was a great pioneer of computational intelligence. He invented evolutionary programming. He held a bachelor's degree from New York University, a master's degree from Rutgers University. He then went on to perform his PhD research at UCLA. He did research on the subject of evolving artificial intelligence. He basically evolved cellular automata. He completed his PhD research at UCLA in 1964. His research culminated in the publication of a book together with Owens and Walsh titled Artificial Intelligence Through Simulated Evolution, which was published in 1966. He founded Decision Science in 1965 and also the company Natural Selection in 1993. Both companies used, and in the case of Natural Selection are still using, evolutionary computation techniques to solve a variety of real-world problems, from bioinformatics to pattern recognition and financial forecasting. He held several patents, including early patents on adaptive noise cancellation and the design of an evolvable neural network in hardware. And I'm sure that you agree that the evolutionary computation community has lost a great pioneer of the field. We now move on with EvoStar 2007. We have assembled an excellent program for you consisting of 163 high-quality papers. This year, we'll be having 3 invited speakers, Professor Ricard Solé, Professor Alan Bundy, and Professor Chris Adami. As I said, we'll be having 3 conferences and 8 workshops. I'm sure there are very interesting talks for every single one of you. You'll be having many opportunities to meet and exchange ideas. Also let me note that we'll be having a joint poster session this afternoon. So now, without much further ado, I'm going to hand over to Ana Esparcia. No.
Hello. How does this go? Oh,
That's this button.
this one? This one. Okay. All right, well, welcome to Valencia, everybody. I'm glad to see most of you made it even on the bus or by your own means. Okay, I'm going to summarize the local information. All this, what I'm going to say, most of it is on the program handbook. But since Jennifer says nobody reads it, then I'm going to say the main points to you. You know, we have, the venue is split in 2 buildings. This building we are just now is 6G. We're only going to do the plenary talks. So it's going to be today and tomorrow, I think it's at 2, around about 2, and the last day, and around about the same time as now. And everything else is going to be on building 7B, where most of you have already been to get your bags and your conference materials. And we're going to have all the conference sessions, plus the poster session, and also the lunches and the coffee breaks. Okay, this is a map of the campus, and here you can see all the buildings. Where we are here is the one down here, 6G. I've also marked the Galileo Galilei as a point of reference. That's the entrance you came through, probably, so you already know that. And across the lawn is 7B. And you also need to know about 3A, which is where the Artscapes exhibition is going to be held. We have the reception there in conjunction with the opening of the exhibition. That's going to be tonight will be around about 7:30. And we have a lot of expectation with that exhibition because we're having the television is coming, national television is going to film it. As soon as I step out of this room, they're waiting for me. And everybody wants to know about the poet robot. And I hope you will all be there and to witness it. And we have also other artists that all of them have very interesting pieces to show. And I hope you will be there to see that. And we also come with the presence of the Conseller de Universitats, which is like the Valencian Minister for Universities and Science. And he's going to do the honors of opening this exhibition. The exhibition will start now, but it's going to run till the 18th of May. But the poet robot is only going to be for the 3 days of the conference. So this is a once-in-a-lifetime thing. Okay, many of you have already experienced the shuttle bus, but for those of you who don't know, there are 4 hotels in the city center where we do pickups. And they start at 8:15 more or less at the Hotel Inglés. And they do the Astoria, the Plaza and the Venezia, and afterwards the Reina Victoria. Today we only use 1 bus. If there are going to be more people interested that weren't there today, it would be interesting that you communicate, you told us, so that we can arrange, because tomorrow there's probably going to be only 1 bus. We used 3 today and they were empty. Also for the independent, we have bus, metro and tram services, which I think all the explanations are in the conference handbook, and otherwise they're on the conference webpage. All these buses will leave you at the Galileo Galilei entrance, including the coach service for the gala dinner will depart from there. Except tonight, after the reception and the art exhibition, there is going to be another bus shuttle to take you back to the hotels for those in the city center. And that one is not going to leave from the Galileo, it's going to leave from the Rectorat building, which is where the exhibition is held. So you should see the buses over there. And all the details for this are in the conference handbook anyway. Okay, this is what I was telling you about, the reception in conjunction with Art Escapes. And it's going to be tonight at half 7. Okay, on Thursday, we have the gala dinner, and it's held in the Masia Chamandreu, which is a 19th century Valencian country house, and it's surrounded by orange groves. And this is all very nice if it doesn't rain. If it rains, it could be a complete disaster, but I hope it doesn't. So let's pray for that. The coaches will depart from the Galileo Galilei at 6:45. And some of them will go, for those of you who don't wait till then, some of the coaches will go back to the hotels to pick the people that could be staying there. If we fill all the buses here, then there won't be any need for that. And remember to bring your dinner ticket, and please advise us as soon as possible of any special diets that you may have, like vegetarian or whatever. If you're not going to use your dinner ticket, please give it back to us so that we can reuse it for somebody else. On Friday, we have an optional trip, which is an excursion to the Albufera Lagoon. This is the biggest lake in the Iberian Peninsula. And the coaches depart after lunch. We will have lunch as usual on 7B, and then we will get the coaches picking up people. Please register in advance, and the price is 12 euros per person. We are also thinking of making before going to the Albufera, making a detour and see all the America's Cup new buildings at the port. So if people are interested in seeing this. The only problem is they do a they have very strong security measures, and it's a bit of a pain. You have to get your belts off and things like that. So we're considering, we don't know if we will do this yet. Okay, and that's all I have to say. And I'm now handing over to Carlos.
Good morning. I'm very pleased to introduce you the plenary speaker who will open the scientific program of EvoStar. We are honored by the presence of Professor Ricard Solé, who is professor in the Cotta Institute for Research, and he's also an external professor in Santa Fe Institute, and who will deliver a talk about the evolution of complexity. And it's a topic, it's quite interesting topic, it's quite relevant to us, to evolutionary computation as a whole, but also has many implications in biology, in economy, in computer science, etc. And precisely, Professor Solé has worked in many of these applications of complex systems, and has actually published his research in journals such as Nature, Proceedings of the National Academy of Science of the USA. So he's really a world-class figure in complex systems, so we are honored by his presence, so please welcome Professor Ricard Solé.
Okay, I think it would be good to have a less light here, if it's possible at all. ¿Podemos bajar las luces? Maybe not. Well, I want to thank the organizers for inviting me to this big event. And I'm going to try to give an overview of some particular aspects of an ongoing area of research, which is complex networks theory. And I choose for that some examples that I think illustrate some of the interesting ideas that go around. And I'm starting with this picture. You might wonder why. It is said that in the old days of exploration, when the explorers reached the end of the world, when the cartography was not complete and there was blank spaces in the maps, named terra incognita, they came back with stories of monsters and strange creatures. That's why this picture here. I'm referring to this strange creature, not this one. The thing is, why we don't see these creatures? You know, when the whole cartography was finished, no creatures, nor strange animals or monsters were there. But of course, in our imagination, in principle, it is possible to think about many things that we don't observe in the real world. And to some extent, the study of complexity involves also an understanding of what is possible and what is not. And this kind of idea actually can be asked in very, very different fields, even in physics. I know this is a very strong question. Is our universe possible? Sounds strange. It seems so, isn't it? We are here anyway. But actually, we can ask that. What I'm showing you here is a large-scale simulation of a very big piece of the universe, which starts with a homogeneous gas of particles and ends up, using the physics we know, ends up in a bunch of very, very complex structures, which actually are more or less what we observe at a large scale in the universe, which is galaxy distributions having a fractal shape. What will happen if we change that? So imagine that we ask ourselves, I'm going to change a little bit the fundamental constants of gravitation or electroweak interactions or whatever. What will happen? What happen is that, and we can analyze that because we have the theory, is that we live in a very, very uncommon place. For example, this picture here shows for two different fundamental constants what would happen with our universe. And what happened is that we live just here in this small dot. And if we change even a little bit the constants, we have essentially something that is unstable. In other words, for a reason or another, no stars with a long lifetime can be formed, and so no life will be observed. What is the interpretation of that? You can interpret that in many ways. Maybe someone, tuned the constants so that we are here. Maybe some people said, since physics predicts that there are actually many, many billions of universes getting formed. We are in one of them where we can live and we can ask ourselves those questions. And some people, and just mention that because I think it's an interesting idea, Liz Molling, a leading cosmologist, has a theory where he says that actually there's a natural selection process going on selecting universes, and our universe actually is an expected one. So in other words, life will be something expected. What about the same question when we go to biology, when we observe complex structures in biology, and I choose this, a piece of the brain cortex as a good example. We observe very complex structures, we observe patterns, and we can ask ourselves again, is this the byproduct of something? Is the product of natural selection? Is the product of optimization? In other words, if you think about, you think about the mechanisms, there are a number of ways of looking at the patterns of evolution. One of them is natural selection, and of course this is one of the most important ones, and I don't think I need to explain in this particular place what natural selection is. In some kind of extreme interpretation of natural selection, we could say that under given conditions, natural selection tries to optimize structures under a given environment. And in some cases, optimization is pretty clear. For example, those networks, those networks of branching, such as your lungs or arterial systems, we know we are having optimized, and we have very powerful theories that explain why is that. Okay? So essentially, it's optimal fractal structures. Is that the case in general? That's I think, a very important question, and I'm going to try to illustrate in one example related to genome architecture that it doesn't need to be the case. An important aspect in this context involves the idea of how much can I get inspiration from human-made artifacts when I see at evolution, at natural evolution. And when I was a student, I remember that often there was the idea that there's some kind of convergent designs both in biology and in technology. But technology is fundamentally different in a number of ways. And François Jacob, in a very influential paper that is still very interesting to read these days, he said that one fundamental difference is that evolution is a tinkerer. So evolution has to reuse things. If you are an engineer, you can go from some kind of design, in principle, to something completely new. And you can just ignore previous innovations. But evolution cannot do that. You cannot say, well, you know, this genome, I don't like it, so I'm going to do something else. That is not possible at all. I'm using these embryos as an illustration because we know that tinkering has been the rule in evolution. And groups of genes that are used to create your fingers are reused afterwards to create some part of your guts, and afterwards also used to create some structures in your brain. So if some particular modules work well, they are used and reused again and again. And actually this, at least in my opinion, is a fundamental problem because tinkering seems to be such an inefficient way of creating innovations. And yet, it seems to work pretty well. And finally, that's more the view of complexity. There's the perspective that maybe many structures we observe that appear in evolution are actually not the outcome of selection. It's more like regularities, universal structures that cannot be avoided, things that emerge once and once again. And I'll show you some examples. And I use Stu Kaufman as probably the pope of these kind of ideas. So the thing is, if you look at complexity, what can you use as a kind of basic framework, a unifying framework? And probably networks, it's really one of the key words here. I'm illustrating these in the following way. This is a painting by Archimboldo where you easily recognize a face. If I show you instead of this picture a bunch of fruits just dispersed, in the end it's the same thing. But of course, making these basic uniques interact properly generates something else. And that's the idea underlying complexity, that I have some higher level structure, some higher level property that cannot be reduced to the properties of the individual units, right? And these, in a very abstract way, can be mapped into a network, okay? And my question is, how far can we go using networks? And how much can we learn about, for example, the mechanisms that drive evolution? Can we understand what parts of a given system are generated by natural selection, which parts by tinkering? It's possible to identify emergence. Well, let's start with just a little bit of theory. When we ignore everything about the topology of networks, of internet, of the genome, of language, we thought, and we were completely wrong, we thought that since many networks in nature emerge from a distributed process, and no one is deciding how to organize it, maybe networks are just kind of a random thing. For example, we can build a network where we have nodes, okay? And the nodes, every pair of nodes can be connected with some probability, right? It's a very, very simple way of defining it. This model was studied for many, many years by mathematicians. And Erdős, or Erdős, I'm not sure what's the right pronunciation, was the star of this theory. I have to say that Paul Erdős deserves a whole seminar, and I strongly recommend his biography. He was an extraordinary creative mind that denies the idea that when you get old, you cannot have good ideas. He had great ideas and great theorems until his last day. And was kind of the big example of an absent-minded scientist. You know, he didn't know how to fry an egg or to take a bus, and this is not a metaphor. And not surprisingly, this kind of so-called Erdős-Rényi networks are very boring. And I know that you guys are thinking, this is actually very boring, but just wait, okay? For example, suppose I take this network and I measure how many elements have one connection, one link if you want, two links, three links, etc. Well, not surprisingly, these networks generate a Gaussian distribution. So almost everyone is around an average connectivity. I know, it's boring. Okay. So are real networks like that? And they are not. If not, the talk will finish here. They are not in two fundamental ways. The first is complex networks, real networks are small worlds. And that connects with something that you experience sometimes. You go in a plane, and the guy sitting just there is the best friend of your best friend in high school. And you say, you see, it's a small world. You know? Is this just an anecdotal thing? It is not. It's fundamentally important. Let's study the following example. This is me, okay? And let's think in a social network. And these are